Okay, this is lesson 3.1b for Mrs. Cucci's College Now Pre-Calculus class. This is the second half of the video of 3.1. So you should be on page 1.17. We just got done talking about the leading term test for polynomials. So what we're going to do is we're actually going to go back over these rules very quickly, and then we're going to go on to the next page. So again, if the exponent is even, x squared, x to the 4th, what you're going to find is that the end behavior as x approaches negative infinity is going to go to positive infinity. And as x approaches positive infinity, the function is going to go to positive infinity as well. Okay? If the leading coefficient is less than 1, meaning negative x squared, negative x to the 4th, as x approaches positive infinity, the function is going to approach negative infinity. And as x approaches negative infinity, the function is going to approach negative infinity. So it has the same end behavior on the right-hand and the left-hand side of the function. All right, for odd, x cubed, x to the 5th, x to the 7th, so on and so forth. If it's positive x to an odd power, as x approaches positive infinity, we're going to go to positive infinity. As x approaches negative infinity, we're going to go to negative infinity. And if I have negative leading coefficient raised to an odd power, we switch that around. As x approaches positive infinity, the function approaches negative infinity. As x approaches negative infinity, the function approaches positive infinity. So again, you have to have those rules memorized. Okay, so on the next page, you're going to find 4 graphs. We're going to use the leading term test to match each of the following functions. So I've got 4 functions here. We're going to match them to my graphs. Okay, so on the next page, here's my first function. We're going to figure out which one this goes to. Now, both my end behaviors are going in the same direction. We're going to negative infinity and negative infinity. Okay, because they're both going in the same direction, that tells us that our functions, the exponent of the function has to be an even. Okay, it's even because the end behavior on either side of the function is the same. They're both going down to negative infinity. Now, since it's going down to negative infinity, that means my leading coefficient has to be less than 0, which means it has to be negative. Okay, so it has to have an even power, and it has to be less than 0. So negative with an even power. So let's go back and look. This one is positive, so that's not going to be it. Here's negative, but it's got an odd power, so that's not it. This one's positive with an odd, so that's not it. So it has to be D, negative leading coefficient with an even power. So the first graph is D. Okay. Second graph. Now, we're going, as x approaches negative infinity, it's going to negative infinity. As x approaches positive infinity, it's going to positive infinity. So this has to be an odd power. Okay. Now, as it approaches positive infinity, it's going to positive infinity, right? As x approaches positive infinity, the function itself is going to positive infinity. Well, we know that from the rules that if I'm approaching positive infinity, it's going up to positive infinity. This has to be a positive leading coefficient. Okay, so odd power, positive leading coefficient. So let's go back and look. Odd power, positive leading coefficient. So that's this one right here. Okay, odd power, positive leading coefficient. Okay, next one. Again, just like this one, when x approaches negative infinity, we are going to positive infinity. As x approaches positive infinity, we're going to negative infinity. So we have to have an odd power. And because as x gets larger, my function is getting smaller to negative infinity, this is going to be a negative leading coefficient. Okay. And while we're at it, let's look at the last one. We're both going to positive infinity on either side, which means we're going to have an even power. And because as x gets larger, my function also gets larger, It's going to be a positive. So this was D, this was C. So we got to decide A, B. D, C, right? This was D, C, B, A. Okay? So that's your leading coefficient test, or leading term test. Okay? All right. So finding zeros of factored polynomial functions. Notice it says factored, already been factored for you. Zeros, solutions, and intercepts, those words are all interchangeable. The connection between the real number of zeros of a function and the x-intercepts of the graph of the function is easily seen in the next example. Okay? If c is a real zero of a function, that means if f of c equals 0, then c of 0 is an x-intercept of the graph. So this is very important that you guys know how to use this rule. Basically what it's saying is, is if this is a 0, this 2 is a 0, if I find p of 2 to equal 0, then 2, 0 is a root, is the x-intercept. Okay, so that's what we're testing for. So in order to do this, we find p of 2. Take 2, plug it in. And we get this to equal -7. Okay, so p of 2 does not equal 0. All right, so we know that it's 2 is not a 0 of the function. Okay, 2 is not a 0 of the function. Now the other one we wanted to try is -5. So p of -5 equals -5 cubed plus -5 squared minus 17 times -5 plus 15. So again, if I plug it in and it equals 0, it's a 0. If it doesn't, it's not. Okay? And when we plug that in, we do get a 0, which means that -5 is a 0 of p of x. Okay? It's that simple to use. Okay? All right. Now, find the zeros of the function f times x minus 2 times x minus 2 times x minus 2 times x plus 1. So we have 5 times x minus 2 quantity cubed times x plus 1, and that's just, you know, we made it a condensed version. It's the same thing. So all we have to do in order to find the solutions is we use that zero product rule. Okay? So we're going to take our functions and we're going to say x minus 2 equals 0. We don't need to write it 3 times because I know with every one of them it's going to be the same. And x plus 1 equals 0. So we get x equals 2 and x equals -1. And those would be our zeros. And we don't have to test those because we know it was already in factored form for us, so that those are going to be the zeros. And that's pretty quick and easy. Okay? All right, find the zeros here. So again, same thing. You're taking our 2. We don't have to write them multiple times because we know we're going to get the same thing. So we get x equals 1 and x equals -2. Now, if I were to write these out, what we'd start to deal with is noticing that we have the same answer multiple times, okay? So we start talking about something called multiplicity. If I have x minus c quantity raised to the k, right? You have some value, like we were looking at before we had x minus 2 quantity cubed, right? If that k, or the exponent, is greater or equal to the 1, there's a factor of the polynomial function p of x, and we have another one where if you were to add one more to that exponent, it wouldn't be a factor. So if k is odd, then the graph crosses the x-axis at c0. Okay? If k is odd, the graph crosses the x-axis at c0. If k is even, then the graph is tangent to the x-axis at c0. So these are two rules that you need to have memorized. If the exponent k, right, is odd, then the graph crosses at c0. If k is even, then the graph is tangent to the x-axis at c0. Tangent meaning it only touches it at c0 once. Okay, meaning it would look something like this. Only touches it once. Okay? And if it crosses it, maybe it looks like this. All right? Okay, so find the zeros of f of x equals x cubed minus 2x squared minus 9x plus 18. So we have to know how to factor these, which we do. We've done this before. This is 4 terms, so we're going to give it a shot as factor by grouping. So you take your first half, and you take your second half, and we pull out our GCFs. GCF in the first half, x squared, and we're left with x minus 2. GCF in the second half is negative 9, x minus 2. And we combine what we have, x squared minus 9, x minus 2, right? What sits out front, what they have in common. And if you look at this, that's factorable again. X plus 3, x minus 3, x minus 2. Okay, so it's all factored out. Now, to find the zeros, that's pretty simple. You take them, you set them each equal to 0, and we wind up with x equals negative 3, 3, and 2. Okay? All right. So, find the zeros of f of x equals x to the 4th plus 4x squared minus 45. So again, we have to factor. Okay? Got to factor it. The way this factors, you know you're going to have x squared and an x squared. Multiplies to be 45, subtracts to be 4. We're going to do 9 and 5, positive 9, negative 5. Okay. Set them each equal to 0. Subtract that 9, add the 5, square root, and we get plus and minus 3i. Okay, hopefully you remember that. X equals plus and minus the square root of 5. So we actually have 4 solutions here, okay? And I want you to take note of something. 4 solutions here, okay? The degree of the polynomial is 4. You should have the same number of solutions as you do the degree of the polynomial, okay? So your zeros of the function are positive 3i, negative 3i, positive square root of 5, and negative square root of 5. Now, only these ones, the real numbers, correspond to zeros of the function or x-intercepts, okay? These are not x-intercepts. If you remember, when we were graphing imaginary numbers, they were on the imaginary plane. So you had to use real and imaginary as your axes. So the only ones that you're actually going to see on the graph are going to be the plus and minus the square root of 5. Okay. So, how do we do this using the calculator? Quick rule, every polynomial function that has a degree of n, so there's your exponent, with n greater than or equal to 1, has at least 1 0, and at most n zeros. Okay, so again, if you have x to the 4th, you're going to have 4 zeros. If you, at least 1 at most, 4 or less. Okay, if you have 3, you're going to have 3 or less. What winds up happening is we wind up seeing something called multiplicity, and we'll get into that a little bit later. Okay. All right, so we're going to find the real zeros of the function f given by, okay, so we are going to do this graphically. I'm not quite sure what happened up here. There it is. Okay, so we're going to find the real zeros of the function given, and we're going to do this using the calculator, okay, because some of these are not pretty, okay? So I'm just going to borrow this, and I'm going to add in a calculator page. So Control-I, or add graph page, I'm sorry. We're going to graph this function. Okay, so as you can see, it crosses through this x-axis 3 times. Okay, shoot. So we have 3 solutions to be had here. This does not like me today. Okay. So what we're going to do is we're going to use one of our tools. Menu, Analyze, 0. Now we've got 3 we have to do, so we're going to have to do this 3 times. Okay, so here's our first one. Menu, Analyze, 0. To the left and to the right. There's my second one. Then again, Menu, Analyze, 0. To the left and to the right. And there's my third one. Okay? So those are my 3 solutions. Okay. All right, so ibuprofen in the bloodstream. Polynomial function m of t equals 0.5 t to the 4th plus 3.45 t cubed minus 96.65 t squared plus 347.7 t can be used to estimate the number of milligrams of the pain relief medication ibuprofen in the bloodstream t hours after 400 milligrams of the medication has been taken. A, find the number of milligrams in the bloodstream at t equals 0, 0.5, 1, and 1.5, so on, up to 6 hours. Round the function values to the nearest tenth. B, find the domain and the relative maximum where it occurs and the range. So we could do this all by hand, but the simplest way to be able to do this is to look at it graphically, and that's exactly what we're going to do. Okay, so again, I'm going to borrow this. We're going to add in a graph page, and we're going to graph the function. Okay. Now, it didn't show up when I graphed it. So what I want to do is I want to hit Menu, Window Zoom, and we're going to zoom fit. And what it's going to do is it's going to bring us not to my function. Okay, we're going to go back to original. So go ahead and do Menu, Window, Zoom Standard, and we'll adjust from here. So we're going to want to go very high here, okay, because we're going to be dealing with 400 milligrams to start with. So we're going to take this Y and make it about 500. You know what? I know what's wrong. Control G. Up. Okay. I have T's in here. I can't have T's. I need X's. That was silly of me. Change those over to X's. There's that last one here, and now this should work pretty for me. Okay, so we kind of see it, right? But I need a better view of it. Menu, Window, Zoom Fit. That's why it wasn't working, because I made it ugly. Okay, so if we're thinking about this graph, we're talking in terms of time, okay? Now, the way I'm looking at it right now is I don't care about the negative time. Anything over here, I don't care about, okay? We don't go backwards in time. So all I'm really concerned about is this over here, okay? And we want to go up to 6 hours. So I really don't care about the 20th hour either. I just care about the 6th hour, all right? So what I can do, and I'm going to make this so it looks better, make that 500. And again, we don't care about negative values. We'll make that -1. So we'll stretch it out, okay? So that's a really nice picture. I just changed the values to kind of fit what we're talking about. We don't care about negative time. We're not going to talk about when we have 0 in the system. We want to look between 0 and 6 hours, okay? If I want to figure out what the values are at 0 hours, at 0.5, at 1, at 1.5, all I really need to do is look at the table, okay? Now, I do want 0.5, okay? So I'm going to have to change my table settings. So now that I'm over in my table, I'm going to hit Menu, Table, and I'm going to edit my table settings and make my table step 0.5. That's going to give me a lot more information, okay? So now I have all of my information for M of 0 is 0, M of 0.5 is 150.115, okay? So I know when it's 0.5 hours, I have 150.15 milligrams in my system. When it's 1 hour, I have 255, and so on and so forth, okay? So we also wanted to talk about what the domain was, the domain and the range, all right? The domain of this function would continue, because it's a polynomial, from negative infinity to positive infinity. Okay? I know in the constraints of the problem we adjusted so that we can only see what we wanted, but this is a polynomial function. Its domain does extend on from negative infinity to positive infinity. Okay? Like I said, we would restrict the domain for the purposes of the problem, but because it's a polynomial, the domain is negative infinity to positive infinity. With our restricted domain, for our problem, we're talking 0 to 6 for our domain. Okay, so restricted domain because of the constraints of the problem, 0 to 6. Now the range, we want to know how high this value is going, and I know that my range is going to start at 0. Okay, so I need to know what that maximum value is. So I'm going to hit Menu, Analyze Maximum. Okay, my lower bound, my upper bound, and it's going to pop up for me. So again, my domain was 0 to 6 for time, right? 0 to 6 hours. My range for the amount that's in my system, we're starting at 0 hours, and I'm maxing out 345.8 approximately. Okay, so there's your domain and your range. And remember, you're using domain and range with your constraint of the problem. You have to think about what you're actually doing and then adjust. Okay. I know I'm over on time, guys. I'm sorry. I guess we will be doing this one in class tomorrow. Okay, so come prepared with any questions that you have. We're going to do this problem in class tomorrow, and I will see you then. Thanks.